So you would have already done casting in your project so far, whenever you want to change from a data type to another data type, or maybe when you encountered any errors or warnings, maybe. So to fix those, I mean, maybe you would have found something like there's a loss of data. There's a loss of data whenever you change from a floating point to an integer point, or something similar. So those sort of warnings are very common whenever you don't focus on what data type you pass as a parameter to another function. So that is when we make use of casting. So casting is basically a conversion process which helps us to change from one data to another data type. And so, for example, this one over here. So I'll just I'll change it to a pointer. Yeah, so you know where. So over here, what we do, I'm taking a floating wave, and you can see I've assigned the value 100.55. And if I try to assign that floating variable, that var underscore float, to another integer variable, var underscore int, as you can see, there is a change in data type because an integer does not take your decimal fractions, whereas a floating point is supposed to take a 7-digit decimal precision, a decimal fraction precision. So when I change it from this floating point to int, obviously the fractional part, so the only thing it gets is 100. So that means I've lost precision there, lost the data there, because when I had 100.55 and I'm assigning it to an integer, I'm giving you all I get is 100. So obviously the compiler is going to throw you a warning saying that there is a loss of there's a possible loss of data. All right, so that is what casting is. Whenever you perform a casting, and this is an internal casting. This is an implicit casting because it is what happens automatically by the compiler, and it's not something that you are specifically asking it to do. It's because you had tried to change the data, and the compiler is taking the effort to make the change. So to avoid such sort of implicit conversions where you encounter warnings, we try to go for explicit conversion so that the compiler knows. Okay, do you guys have any problems listening to the audio part of the lecture? Because I keep getting okay. I don't know. Is it something wrong with my internet connection? So you can't hear me. Okay. All right. Let me try. Let me try disconnecting and connecting it again. Then just give me a minute or two.
I want you to all pass this class. Very nice.
That was unexpected.
That was it. Everyone. Now that while we're waiting, we can sing. What's his name?
Ash.
Ash, his happy birthday.
Oh,
Yes.
Happy
yes.
birthday, big boy.
No, we can't.
Oh.
Classes start
after,
again. Okay.
after.
Somebody's birthday today?
Yeah, it's
Ashley.
Ash's birthday. Can we all sing happy
Oh,
birthday?
Actually,
okay.
yeah,
Happy birthday, Ash.
Thank you.
yeah.
All right. Maybe we can, yeah, have a little happy birthday singing after an hour or so.
Yes,
Can we
yes.
get TTS to sing it?
He has to
Everyone,
sing it.
everyone is.
Okay, so let's just wait till maybe around 10:30. Okay, so are you able to hear me clearly now?
Yep, I can hear you.
Yeah. Yes.
Okay, all right. Too many updates in Discord. Okay, yep. So we were talking about implicit conversion. Implicit conversion is when you don't specifically tell the compiler that you want to convert from one data type to another data type. And then it happens
Yes,
automatically.
Can I ask you a question? Why do we need to
Yeah.
convert one to another? In which cases?
In most of the cases, it happens when you use the predefined functions. Like you've seen many math.h and CSTDO functions. So I believe you would be using one of those functions for your projects at least. So in those cases, um, the arguments expected by these functions might be something different from what you are passing. Like maybe you are passing an integer variable, but the argument expected there is a floating point. So in that case, if you would if you were to just send an integer variable, the compiler would show you a warning saying that you're not passing the actual data type, the expected data type. So it might be something like possible loss of precision or possible loss of data or something similar to that. I am sure you would have encountered some warning of that kind. So these sort of conversions is called the implicit conversion, where the compiler is just converting it for you. That's why it's better if we do a conversion so that the compiler understands that, okay, this person knows what he's doing and he has converted to the appropriate data type. And then basically that avoids any warnings. All right. Okay, so I'll just move the pointer again. All right. So we just see how explicit conversion is done. I'll So one of the warnings that you get is something similar to this, like conversion from float to int, possible loss of data. So the warnings are basically helpful to understand if you have coded your program well, if you have not changed any data type from. So in a case, I mean, though you might encounter lots of warnings, it is in one way helpful because this helps you to understand whether you are losing any data or not, whether maybe your expected data is not calculated in the same manner that you would expect, and this would be one of the reasons because you've lost some value there. When 100.55 becomes 100, obviously there will be change in the resultant value. So for that, what is important is you should try to use the correct data types whenever possible and avoid these warnings. Or otherwise, if you're not able to use the exact data type, you might need to go for explicit conversion. Explicit conversion is when we tell the compiler explicitly that we want to convert a value, when we want to convert the data type of our variable into another data. Like for example, what's seen here. So here I have an integer variable n is equal to 200, and I'm trying to do an n by 100 operation. So n by 100 could result in a fractional value, and I'm assigning this to a floating point variable. So when I assign it to floating point variable, if I were to do just float f is equal to n by 100, this would give me the same warning saying that there is a possible loss of data, or the data types between the two sides do not match, or something similar to that. So rather than get those warnings, what I'm telling is just convert this n to a float, and that's why I have this in parentheses over here. So in parentheses, I'm clearly saying float, which clearly indicates to the compiler that I'm doing an explicit conversion and I know what I'm doing. All right. So this is the only thing you need to do in case of explicit conversion. Just give your data type in the parenthesis there before the variable that you want to cast. So n was an integer, which I want to cast to a float so that this happens without any warnings. All right. So have you understood the basic explicit casting method? Just
Yep.
give the data type in parenthesis. Okay. So there could also be some functions which actually takes generic. Do you understand what this argument means? Void star p data, void asterisk p data. Do you understand what that means? Any
So
guesses? What does the asterisk sign indicate? This one, this
It's
asterisk sign here.
a pointer.
It's a pointer. Yeah, that's right. Um, so if I say something like int asterisk p data, what would that mean? Instead of the void, if I have an int, if I have an integer that is int asterisk p data, what would that mean? You can message too if you don't find comfortable talking anyway, but just an attempt. What does int asterisk p data mean? Yeah, that is a pointer that you would expect to point to a integer variable, point to an integer variable. That's why we declare it as an int asterisk p data. So when we say void asterisk p data, void indicates that we are this particular pointer could point to any data variable, any data type. That's when you declare a void. All right, because you specifically don't know, maybe you don't know which type of data type you want it to point to. So just declare it as a void asterisk. A void is not a commonly used one, but for functions that is like sort of generic functions which could be used for multiple data types, you might go for a void asterisk. So these sort of pointers can point to any or it can hold the address of any data type. So over here, this particular generic function has a pointer which we don't know whose address it's going to hold. And we also have a data type. So this is an enum. So this data type enum, this enum data type will specifically tell us what is the type of the data that is that this pointer points to, so that it's clear to the compiler that which is the data type that is coming into this function. All right. So if you have if you have something called a character text, which is equal to hello world, and I want to pass it into this I want to pass it as an argument to the write line function. What I would do is I would pass data type as the one of the defined data types in this data type enum is wl underscore. So which indicates that it is a string data type that I'm passing. So the first argument there clearly specifies what is the type of the data, and the second argument is the address of the data that I want to pass. All right. So as you can see, I've not used an ampersand over here to indicate that I'm sending the address of text. Why? Because this text is an array. And like I said, an array's name means the address of the array. Implicitly indicates that you're sending the address of the array. So whenever you're passing an array, you do not need to give it as an ampersand. You can directly just say the name of that array. And this is only for arrays. This facility is only for arrays. If you were passing variables, you would need to give an ampersand there. All right. Let's see another example. So in this example, I've got a floating point variable. So yeah, floating point f value. And since I'm passing a floating point, the data type enum that I'm passing will be something called wl underscore float, which indicates that the data I'm passing is a floating point. And as you can see, the second one will be passing an address because I wanted to send an address to this pointer. I want to pass the address of f value, but what am I doing? Since the pointer, since the type of the pointer is a void pointer, I am explicitly typecasting it to void asterisk in brackets. So this is an example of an explicit typecasting. Even in the previous case, What was I doing? I am explicitly typecasting the text to void as using the same explicit casting method. So same thing if I have another data type. So this is basically a user-defined data type. So I briefly mentioned about user-defined data type in the previous class, I guess. So this is a user-defined data type created using a concept called class, which is a very important concept, and we'll be seeing it when you come back after your term break. So this is the type of mat world over here is C matrix. So the data type that I'm passing is something called WL underscore matrix, which is a defined data type in the enum data type. And when I pass the address of this mat world, as usual, I need to typecast it to void asterisk because that is the expected type. Remember, I could also pass I could also pass simply address of mat world. It will still not throw me an error. It will give me a warning saying that I'm trying to convert it from a C matrix type to a void type. To avoid these warnings, to tell the compiler that I know what I'm doing, I am trying to actually convert it to that. I actually want the void pointer to hold it. I'm explicitly giving this explicit conversion in parentheses. All right. So hopefully you've understood how you could cast from any type to any type. Just get the data type that you want to convert it to in parentheses. Okay. So basically a void asterisk is just a pointer to an arbitrary data type if you're not sure of what data type that you want to hold. And while I was discussing pointers, I'm not sure if I mentioned it, but a pointer variable, the size of a pointer variable is always going to be 4 bytes. Okay, so whatever the type is, whether it is an integer pointer or a character pointer or a void pointer or any type of pointer, it's always going to be 4 bytes. Because the purpose of that pointer is just to hold the address. So that is going to take 4 bytes no matter what. All right. So I'm moving forward, assuming that you guys are okay. If not, just ping me. Okay, so now we're going to C++ specific style casting. So what we discussed now was an adaptation from the C casting methods. C casting methods, the only thing that you need to think of is put the data type in parentheses. And that is applicable for C++ as well, because C++ is just an extension of C. But C++ provides 4 additional type of casting methods, which is what is given over here. So you've got the static cast, the const cast, reinterpret cast, and dynamic cast. So the reason we have different types of casting methods is so that we can put in a little more restriction where required to the different types of casting. All right, so that we don't, so that these casting, no, I mean, depending on what casting method we use, there is a little amount of restriction for each one, so that there is an implicit check in case you don't follow the rules, it should at least throw an error. So let's start off with the first one, that is the static cast. And the format is you have the keyword static underscore cast, and in these angular brackets you just specify the type, that is the data type that you want to cast it to. The next one, the expression in parentheses, is basically the variable that you want to cast it to. So as you can see this example over here, if I want to convert from an integer n to a floating point f, I would do static underscore cast. In the angular brackets, I'm giving it a float because I want to convert it from integer to a float. So my end result is I want to convert it to a float. And that's why I have float in angular brackets. And the variable that I want to convert is, all right, so that is the expression in parentheses. These C++ casts are more explicit. They explicitly say what you want to do. But why do we need to do a static cast? Why can't we just do a normal casting method where we just give the type in parentheses? We'll see in the next slide. All right. So static cast basically helps us to convert between only related pointer types. So that is the main thing about static cast. So when you say related pointer types, you could do from floating point to integer. You can try out other types and see whether static cast gives errors in case of any. That's an exercise for you. So try out static cast and see whether it gives you an error in any case. All right. So usually it will convert between all built-in data types, even when there's a loss of precision, the same as you would do for the same as what would happen for a normal C-type casting, where you would just give the data type in parentheses. All right. So right now you've not learned more. You all you know is just built-in data types. You don't know anything about user-defined data types. So when we come to that, you'll understand better about what it means when it says that you cannot convert it to a type outside of the hierarchy. So when we discuss about user-defined data type, you will be creating hierarchies there where one is created out of another type and so on. So whenever there is a hierarchy which is not part of an existing hierarchy, whenever there is a type that is not part of an existing hierarchy, static cast does not allow that conversion. So this restriction will be more clear when we discuss about those user-defined type. All right. Otherwise, for the built-in types, this should allow you to convert between most of them. Now coming to the const cast. So const cast, like the name suggests, it is something to do with the constantness of the expression. So if you have a variable which is a constant variable, you know what a constant variable is, right? Constant variable is one whose value cannot be changed. So if you have a variable which is a constant variable, you can temporarily remove the constantness of that variable. All right, because maybe you want to change the value of that, I mean the current value of that variable, or you want to make some change to it. So what it does is it changes the constantness of the expression and it casts the constantness away. So generally it is used whenever you want to convert from a const to a non-cast or to a non-const. Because if you try to convert to a non-constant to a constant, it doesn't actually matter. All you need is just to create a constant variable. That doesn't require a conversion. But a constant variable, if you want to make it to a non-constant variable, then you will need to go for a const cast. All right. So obviously, the reason you've defined the reason you've declared a constant variable is because you don't want anybody to touch it. Like for example, you have for your game you have the number of lives, that is a maximum number of lives that the player. So you know that, and you're saying const max lives is equal to 5. What is the reason for that? You know that wouldn't change in the game. So if I try to change the number of lives, then obviously I am doing with the basic design. I am doing away with the basic design of the game. So you are doing something that does not fit with the current program design. So using constant cast basically should make you think whether you do need to change this or not, because you are trying to change your initial design where you're changing the constant value. So be very careful when you use this, because if you were to use it very frequently, then that doesn't make any sense making that variable a constant variable. All right. So I hope you've briefly understood what const cast means. It removes the constantness of that variable. All right. So there are a few exercises that will from where you can clearly understand. So maybe after we are done with the lecture, we'll just have a brief look at the exercises. Otherwise, shall I move forward? Okay. So coming to reinterpret cast. The reinterpret cast will help you to convert from any type to any type. All right. That is, it basically plays from the low level. It basically plays from the bit level. So it converts from any built-in type to any other built-in type, from any pointer type to any other. So this helps you to do any sort of conversion from anything to any other possible thing. And that's why it should be used with extreme caution, because you are playing with the low level over here. You're playing with the bit level over here, and you don't want to make any any problem with your system. So you're playing with the basic device level, and that's why this should be used with extreme caution. All right, that is only if you need it. The way you would use it is, the format remains the same. You have the reinterpret underscore cast over there as your keyword. In angular brackets, you specify the type, and then in parentheses, you give your expression. That is, maybe it's just a variable. And the format for all type of casting methods remain the same. But in the case of reinterpret class, make sure you only use this when absolutely necessary, because why would you need to change the device level data unless you're doing something at the device level itself? All right, so that is about the reinterpret cast. And coming to the dynamic cast. So dynamic cast is a very common usage in case of user-defined data types like classes. All right, it's a very frequently used type of casting method. So dynamic cast helps you to perform a conversion whenever possible in a hierarchy. So like I said, a hierarchy is created whenever you create a user-defined data type, then you create another user-defined data type from that existing one, and then you can create another one, and so on. So it's like saying, suppose you have a user-defined data type, say vehicle, and then I create a car from that vehicle. All right, I'm creating a new data type called car from that vehicle, because car will obviously have some features of the vehicle plus some additional features of its own. And another one I could have is a bus. So a bus is again another type of vehicle, but it has something different from a car. It could have some, obviously it has some different features from that of a car, at least the number of wheels. So these are different things that I could inherit from the vehicle class. So what the dynamic cast does is the dynamic cast checks if the conversion I'm trying to do is within the same hierarchy or not, and whether the conversion is possible or not. Like for example, conversion between a type bus into a type car may not be possible, because as you know, a bus is a huger vehicle than a car. A bus has more number of wheels than a car. Bus has no more number of seats than a car. So if I try to convert from a bus data type to a car data type, that may not exactly be possible. So dynamic cast does a detailed check in that manner. It not just checks that they are in the same family, it also checks whether the conversion is actually possible or not. All right. I know you're not familiar with class at this stage, but the reason I gave you this example is just to understand how dynamic cast works, at least to roughly understand that. All right. So in the case of dynamic cast, the cast is either successful if the conversion is possible, or it will give you a compiler error. So you will know whether the conversion is possible or not. Plus, another thing is dynamic cast does checking at runtime. So when I say at runtime, that basically means based on the input data, there will be some each variable will have a value. So that value is at runtime, because that happens whenever you run the program. When you run the program, a variable has a particular value, depending on what the value the user gives it. The user gives a system. So based on the value contained, dynamic cast will decide whether the conversion is possible or not. All right. So that is how dynamic cast is different from the other casting methods. Dynamic cast is a runtime casting method, whereas the other casting methods are all at compile time. So at compile time, when I say at compile time, the compiler knows what the values are. The compiler just checks it out and then just cancels C. And then maybe if it is an error, it throws you an error. Otherwise, it performs it. But dynamic cast works at runtime. It checks for the value in there and then sees whether the conversion is possible. If not, it just gives you it does not perform the conversion, and then it returns a null pointer. as it's given in the last line over here. So in the case that is not possible to convert between the two types, the cast fails and returns a null point. And since dynamic cast is different from the other casting methods and it happens only at runtime, a runtime type information should be enabled in the compiler. That is an RTTI. All right. So we'll see more about it later. For now, just understand what the different casting methods are, because you wouldn't use a dynamic cast now since you've not started class concepts anyway. All right. So did you briefly understand what dynamic cast means? Any doubts? Anything you want to message me? All right. So there are no messages now. So I assume you're all okay. Okay. Yeah. What is it, Callum? Do you want to go? Do you want to unmute and ask me?
Sure. What's the application? Why would you want it to return a null pointer if it's not possible to convert?
If it's not possible to convert, the null pointer basically indicates that the conversion has not happened. So when I do a conversion, and I will be checking for that, I will be checking for whether there is a null pointer returned or not. Because if a null pointer returns, then I know that the conversion has not happened, and I won't go ahead with the actual steps. So it's like a validation check. So I try to convert, like for example, I try to convert from a bus data type to a car data type, and then the dynamic cast decides that this conversion is not possible, so it returns me a null pointer. What I do is I check, okay, is the return pointer a null pointer? Yes, then in that case, just throw an error saying that, sorry, the conversion is not possible.
Right, but
that is to help me understand whether the conversion has actually happened. Now, if the conversion has actually happened, if the bus type has converted to a car type, then I'll be making use of that new converted value and using it for the further steps in my application.
right, so it's about bringing the errors up.
Yeah,
so
it's
you can-
about
okay.
it's not a compile time error. It is not going to show up on your screen. It is going to be a runtime error. So this runtime error, so since it is a runtime error, I need to catch it in my code. I will need to do a check. So if the return type is, or if the pointer. So basically, we are all dealing with pointers now. So if the pointer is equal to a null pointer, then see out the conversion has not happened. Else, perform my actual steps. So maybe now I'm using my new converted pointer to I'm changing the value of my new converted pointer, saying that this should only contain 6 seats, and so on. So that is the reason this null pointer is very important. It's like your validity checks whenever you do, like for example, in your slot machine, you're saying if the user has not, you've asked the user to enter the menu options from 1 to 3, and if the user has entered some other option, say 10, some other value in there, say 10. So you would do a validity check to see if the menu option is equal to 1, or if menu option is equal to 2, or menu option is equal to 3. Only in those cases it should execute whatever you do in your game. Otherwise, it should show me an error, right?
Right, okay.
Okay, yeah. So that is the only purpose of a null pointer, to see whether to understand code whether the conversion has happened or not. And if the conversion has not happened, you take the relevant steps for it. Okay. All right. So everybody else is okay? Okay. In that case, I guess that is the end of the casting methods. All right. So for this project, what you would basically need is probably just you could try the static cast method. You could also use a C casting method, which was the simplest one. So that's up to you what you try to use, but you wouldn't need any other casting method. Of course, you have the cons cast, but I wouldn't recommend that, because cons cast should be used only if it is absolutely necessary. But the one type of casting method that you could use is either the normal C type casting method, if required, only if required. So you're not required to use it if you don't want it. All right. So basically, look for your warnings. Like I said, in your project, I'm expecting you to remove all your warnings. Okay. If you're not able to remove all of them, at least try to work on most of them after you have totally completed your game and made it error free and made it functional. So yeah, if many of the warnings would be because of the casting problems. So those can be fixed with either the C style casting method or using the static cast, which is a more specific C++ method. All right. So can we move on to the constant pointers in that case? Any doubts before that? A few of you have gone on unmute. So do you want to ask me something? Everybody okay?
Yep.
All right. Okay. In that case, let's go ahead with constant pointers. Okay. So constant pointers makes use of the const keyword as we have always done for any constant variable. And then we'll also be discussing about what type def means and about something called function pointers. So this is how you would define any normal constant variable. You give a const keyword there before the data type, before the declaration of the variable. So I have a float k pi. So as you know, the pi variable only has the value of your pi variable is 3.14, and that's always going to be a constant variable, and that's the reason I've given it a const keyword before that, because I do not want anybody to modify it accidentally, and it's also an indication to everybody out there that this is a constant variable which should not be modified. So similar to that, we also have something called constant pointers. But as you can see, we have different types of const declarations in here. So in the first case, you have got something called const int asterisk pi1. The second one is int asterisk const pi2. Then the third one is like const everywhere. So you've got const int asterisk and const pi3. So what do each of these declarations mean? So in this case, what it means is pi1. So you should learn to read the pointers from the right hand side to the left hand side. So start off from the right hand side. That is the opposite side of from where you would start writing. So pi1, and then go backwards. You would see an asterisk there. The asterisk indicates that it's a pointer. So pi1 is a pointer to a constant int. That is a constant integer value. All right. So that is the meaning of what this is. pi1 is basically a pointer that will hold the address of any constant integer variable. So what does a constant integer mean? The variable will not change its value in any case. So the purpose of pi1 is to hold the address of such constant variables whose value is never going to change. All right. So the value pointed by this pointer is never going to be changed. So if I do something like asterisk pi1 is equal to 5. So what does this mean? This means, I hope you remember dereferencing of pointers. If you were to use asterisk sign when you were creating a new pointer variable, when you were declaring a new pointer variable, that means that you're indicating that this is a pointer variable that you've declared. But in every other place where you use an asterisk before the name of the pointer variable, then that means you're trying to dereference it. All right? Dereferencing means getting the value inside the address that it is holding. So pi1 is holding the address of some constant variable. pi1 is holding the address of some constant variable. And I'm trying to do asterisk pi1. I'm trying to access the value in the address that is held by pi1. So if I do asterisk pi1 is equal to 5, I'm trying to change that value of the constant variable. But since I said it's a constant variable, obviously I cannot change the value of that. And this will throw me an error. So in that case, does Jake have any doubt? He is typing something. Okay, all right. So yeah. So can you guess what this one means? Of course, it's already written down there. Does int asterisk const pi2 mean? Go backwards, like I said. pi2 is a constant, right? So go backwards from pi2. pi2 is a constant asterisk. So it's a constant pointer to an integer variable. Or in other words, pi2 is a constant pointer that holds the address of an integer variable. So how is this different from the previous case? In this case, your pointer itself is a constant pointer. When a pointer itself is a constant pointer, that means pi2 can only hold the address of this particular integer variable. I am not allowed to change the value of the pointer pi2. Okay. So let me just go to the previous slide just to compare the two. In this case, what I said is pi1 is a pointer to a constant integer. So when I say pi1 is a pointer to a constant integer, I am allowed to change where pi1. So suppose I have got two constant integer variables. So I have constant a is equal to 10 and constant b is equal to 20. Now, first pi1 is holding the address of a. I'm allowed to do that because pi1 is supposed to hold the address of a constant integer variable. So I'm saying pi1 is equal to address of a. So that's totally fine. And then I decide, okay, now I don't want to hold the address of a. I want pi1 to hold the address of b. So I would do pi1 is equal to address of b. Okay, so as long as it's just holding the address of a constant integer variable, it's totally fine. But in the second case, when I say pi2 is a constant pointer to an integer variable, what this means is I cannot change the value of pi2. I cannot change the address that pi2 holds. So if I say int asterisk const pi2 is equal to address of some integer variable x. So if I say int asterisk const pi2 is equal to x, I cannot at any other point say pi2 is equal to address of y. Because since it is a constant pointer, I am only allowed to give it a value at the time of declaration. I cannot change its value at any other point. Okay, so what is Callum saying? Is the relationship between reading right to left about what's on what side of the asterisk? Yeah, it is. So that's the reason I'm asking you. It's easier if you read it from right to left, because in that case, you can clearly understand what is the meaning of that pointer declaration. All right. So in most of the variable declarations, it would be best if you try to read from right to left. It just gets complex whenever pointers comes into picture. So then in this case, I have to specifically say that please read from right to left. So that will be easier, especially in these sort of complex looking declarations. All right. So like the example says over here, the integer value can be changed. So pi2 is a constant pointer to an integer. So this means the integer that it is pointing to, that integer value can be changed. That doesn't matter. The pointer itself cannot point to any other variable because it is a constant pointer. All right. So the integer can be changed, but pi2 cannot change to anything else. All right. So if I have something like asterisk pi2 is equal to 2, which means I'm dereferencing pi2's value. I'm changing the value that is contained inside the address to 2. That is fine. I can do again asterisk pi2 is equal to 5. That doesn't matter. Because this is dereferencing the value inside the address. The value inside the address can change because it is a normal int. But if I do something like pi2 is equal to 0, here I'm trying to change the address that is held by pi2. So that cannot be changed. I hope you can understand the difference between these two statements. In one statement is asterisk pi2, which means I'm dereferencing the value of pi2. The second case I'm doing pi2 is equal to 0. Edit the address that is held by pi2. So that is not allowed because a constant pointer cannot be reassigned to a new memory address. All right. So are these two declarations clear? One is a pointer to a constant integer. The second one, constant pointer to an integer. All right. So let's see what the last one means. So you can see const everywhere over here, which basically means this is a combination of the two previous ones. So here pi3 is a constant pointer to a constant integer. So I'm reading backwards now. pi3 is a constant pointer to a constant integer. So what this means is neither the address contained in pi3 can be changed, nor can the value that is pointed to by pi3 by the nor the value that is pointed to the address pi3 can be changed. All right. So it is a constant point plus it is a constant integer at that address. So the value that is pointed to cannot be changed, and pi3 also cannot be changed to point to anything else. So you have two constants there. So basically, you cannot do anything with this. All right. Have you understood this? Constant pointer to a constant integer. So read it backwards always. It'll be much easier for you to decipher what it means. All right. So any doubts? Okay. Okay, Callum. Yep. Do you want to go on unmute? So I'll just wait for Callum's message. Why would you use a constant pointer to a constant integer instead of just using a constant integer set in the loop? I'm not exactly clear with the instead of just using. Can you unmute yourself and just
Okay, cool. So
Yeah.
like,
Yeah.
why would you go to the effort of using a constant pointer that always points to the same constant value instead of just using that value?
Generally, like like when we discussed pointers, like I said, one of the main uses of pointers is when we want to pass the values to functions. So in this, I mean, when I pass it as an argument to a function that takes a pointer, one of the reasons is I don't want it to unnecessarily create a copy of a variable, and that's why I do passing by pointers, and because I don't want anybody else to change the value in that particular function.
Right, but if
I
you're
am declaring it as a total constant. Yeah.
yeah, sorry, what I mean is because it's a constant,
Yeah.
like, and because you're only pointing at that constant, then that value is not going to change.
Yeah.
So why would you need to point to it instead of just using that value?
You could also just use that value, but the thing is, like I said, whenever I pass these values as probably I want to make use of these values in functions. I would want to, maybe for some reason I want to use this value for some other calculation which doesn't affect this variable. So whenever I pass values to functions, the normal default procedures, it creates a copy of the variable. So whenever we have memory constraints, we try to reduce any copies that is made unnecessarily. So that's why we make use of pointers, so that there is no unnecessarily memory wastage that happens. The pointer basically points to the same value, and if you declare it as a constant, it makes sure that you don't change this value itself. So that is one of the reasons that where you would go for a constant pointer, because you want to pass the values by pointers, you want to pass any arguments by pointers, you also don't want to make any changes to those values. Does it Does it? Does it roughly make it clear?
Well, I mean, just like an int is what, 4 bytes, and so is a pointer.
An int is a 4 byte. Yeah. In this example, probably what I said may not make any. Would not save the memory as much as you would think. But suppose I have any user defined type. So maybe that user defined type is like maybe around 20, maybe about 20 bytes or something. So when I pass that 20 byte variable, 20 byte user defined variable to a function, I don't want it to create another copy in that called function. So that's where I would use a pointer to hold the address of that variable that I'm parsing. So when I create a pointer, the pointer just takes 4 bytes. So 4 bytes of memory just to hold that. The same, just to point to the same user defined variable that I'm sending. User defined 20 byte variable that I'm sending.
Right. Okay. So it's about memory conservation.
It's about memory conservation, yeah. Right, where I want to pass a value, but I don't want it to create another copy. But I also want to make sure that these values does not get changed, because when I create pointers, I'm giving it I'm giving it a more I'm giving it higher power to access the value over there. So to make sure that there is no change happening anywhere, I would declare it as constant. So depending upon how secure you want your system to be, you can declare constants wherever it is required. All right. So I know it's a little difficult at this point to understand without examples, but since you have only defined only learned use only defined only learned about built-in data types at this point, I can only roughly explain it because I don't want to move into user-defined data types at this point. All right.
Okay. So there are bigger data types that use a lot
There
more
are
memory than
that
just
you
4
create,
bytes.
yeah, because you could create a data type. 20 is just a minimum. You could maybe go up to 40 bytes or even bigger than that. A single data type could be even 40 bytes. So that is what you create using classes. Okay.
Okay.
All right. So that's when you really have to focus on the memory. All right. So I guess I can move ahead in that case. Okay. So it basically protects the parameter that is being passed, so that the function, so that does not allow the function that's being called the ability to change the pointer's address. Okay. So neither the pointer's address is being changed nor the value that is held by the pointer. So const is generally used in the case of these. Not generally. If you have something like constant, like health, or what else, like the maximum score, or something in that sort, you would make use of constant or lives. But in other cases where you would go for const pointers, it is usually whenever you pass arguments to functions, because you don't want those functions to change the values that you're sending, and neither do you want it to create another copy, causing any memory wastage. All right. So that was about pointers, constant pointers pointing to constant variables, and so on. So the only rule that you need to remember is read backwards, or read from the right hand side, from the rightmost. Okay. So your variable pi3 is a constant pointer to a constant integer. So always make it a habit to read backwards. Okay. And now coming to what type def means. So type def is a short form for a type definition, or you can also say as alias or a synonym. So it basically helps you to create a new name for your types, the data types. So if I say something like type def char int 8, you can, type def char int 8. You can either call your char data type as char, so you can say char char a is equal to or char x is equal to a character a. But you can also say int 8 x is equal to character a. So I'm creating a synonym for the same data type. Or you have type def unsigned char uint8. A uint8 x is equal to character A. So these are basically synonyms that you can create for the existing data types or for user data defined data types. Whenever we have any rules for the for the built-in data types, remember the same rules apply to user defined data types also. So every rule that you have here will be applicable to user defined data types that you learn later. So you have type def unsigned int, which basically is uint32. So one of the reasons why why you might go for a type def is, one reason over here is because, see, as you can see, you have uint32. So uint32 basically helps me to understand, okay, uh, how many bytes are there for each data type. So if you want to make it more clear to maybe the programmer, that how many bytes of data it can hold, you can do that. All right. Sorry, it's not bytes, it's bits. So how many bits of data it can hold? You can do something like uint32. So over here, as you can see, char is int8. So this indicates that there are 8 bits of data. Or in the case of float, type def float 32. So you know it's a float variable, 32 bits of data. So that is one reason why you might go for these sort of aliases. Another reason is maybe your data type is too big. Maybe like something like unsigned char. So you don't want to write unsigned char a every time, or unsigned char x is equal to character a. You want a shorter alias for that. Say uint8. So that is a much shorter version. Or another reason is probably the company that you work for has some coding standards. So it has its own specific alias or type def for all the data types that the company uses. Okay, so to make it standardized throughout any project that is done in the company, you would go for a type def there. So there are multiple reasons why type def might be used. Okay, so that is about type def. We'll be seeing one more example of type def after we have seen function pointers, which is the next topic. But I hope you have understood what type def means. It's just an alias that you create for a data type. All right, so you can give any name over here. You can also give your name in here. It doesn't matter. But then, of course, don't give for our actual projects. We would expect you to give meaningful names, which can be understood by everybody else. So, coming to pointers to functions. So far we have seen pointers to variables, a pointer to an integer variable, a pointer to a character variable, a pointer to a floating point variable, and so on. But we can also have something called pointers to functions. All right. So when we see pointers to functions, what we need to remember is, like I said, for an array name does not need to indicate an address sign over there, because an array name itself means that you are talking about the address of the array. So similarly, a function name, if you use a function name implicitly means you are referring to the address of the function. So even in the case of a function name, you wouldn't need to specify an ampersand over here. You wouldn't need to say address of the function. You can just say the function name. Okay. I will, after I've just shown you, after I show you what how pointers to functions can be created, I'll tell you what is the need for this. But let's just see how we can create a pointer to a function. All right, so it is also possible to create a pointer variable that points to a function, and using that pointer variable, you can even call function. So you can see how far pointers can go. All right. So the only tricky part is creating a function pointers. So in the case of function pointers, now if you talk about an integer variable, how would you create a pointer to an integer variable? All you need to do is just say something like int star ptr, which clearly says that ptr is a pointer to an integer variable. So here the only thing you need to specify is the int data type over there. But in the case of functions, there are a number of things that you need to think of. A function has a forget about the function name. That is not important in this case. But what you need to remember is signature. The signature means the argument list. So how many arguments it has? What are the types of those arguments? What is the return type of the function? So these are the important things in a, and that is what you will need to specify whenever you declare a pointer to a function. All right. So this is an example of a pointer to a function. So what does this mean? Here function, here func p is a pointer because I'm reading it backwards, is a pointer. This is indicated in parentheses to indicate that this is a function pointer. So this is a function pointer that points to a function returning a long and that has integer as a parameter. All right, or you can say func pointer is declared to be a pointer that points to a function that takes an integer parameter and returns a long. So this parenthesis around this function name, around this asterisk function name, is very important because that is the only way that you can specify, you can indicate that this is a pointer to a function. If you don't give this parenthesis, it means something else. All right. So the parenthesis around this binds it and says that this is a function pointer. So in the case of a function pointer, this argument list is important as it is for any function. In any function, you would find the parenthesis containing the arguments, right? So you can have one argument, you can have two arguments, and so on, depending on how many arguments that function takes. So this argument list is important, and the return. So this particular function pointer can only point to those functions which takes one integer argument and returns a long data type. All right. So have you able to understand what this means? So if you have some functions like um, long func, say something like what do you say, long calculate area, and in brackets you've got int radius. Then this function pointer can point to that function, because in the function that I've just given now, the example that I've just given now, which is long calculate area, and the argument is an int radius, type is the same, that is a long return type. The argument list contains one integer, yes, so it is valid to be a function that can be pointed to by this function pointer. All right. So any doubts in understanding this particular example? Over here, func pointer is a pointer that points to a function that takes an integer variable and returns a long. Okay, Bravo, do you have a doubt? Do you want to go? If you want, you can unmute yourself and ask the question. So when you set up this kind of pointer, it is set to a type of function, not related to no, it's not related to a specific function. I mean, of course, it is related. It is related to a type of the function. Yeah, that's how it would be a better way to describe it. Because when you say type of the function, you are you are defining it based on how many arguments, on what type of arguments it holds, and what is the return type. So I could have multiple functions which have multiple in which maybe I have got something called long calculate area, and in brackets I've got int area. Then I've got another one, long calculate marks, calculate total marks, and in brackets I've got int mark. And what else? Long calculate score, long calculate total score, and in brackets maybe I have int current score. So in each of these cases, it's the same argument that I have, that is an integer argument, and it's the same return type, that is the long data type. Pointer can point to of these functions. All right. I hope that is clear, at least for this example. Okay, I guess nobody's typing, so I'm just assuming that's okay. And I'll go ahead. So can you see these two declarations over here? I know the descriptions are written below, but then have a look at these two declarations and try to have a go yourself before looking into the description below. So in the first case, as you can see, there are no parentheses. So one main rule in pointer to functions is you need to have the parenthesis about the function name that binds the function name and the asterisk. But in the first example over here, there is no parenthesis. So what does this mean? In the first case, this function is a function whose name is called function, which takes an integer argument, which returns a value which is pointer to a long. All right. So the value returned by this function is some pointer variable, which points to a long data type. Do you understand what the first one means? This is a normal function. The first one is the normal function, which takes an integer argument and which returns a pointer to a variable of type long. What about the second one? So the first one is not a function pointer at all. It is just a normal function which returns a pointer that holds the address of a long data type. Whereas the second one is a function pointer because the parenthesis binds the name and the asterisk clearly. So the second one is a function pointer. So it is a pointer to a function that takes an integer variable and returns a long. So this is a function pointer that only points to those functions which takes an integer argument and which returns a long data type. Returns a long and is not a function pointer. Right? The second one returns only a long data type. So yeah, Jake, for the first example, does that mean the result of the function becomes the name of a pointer that references? Yeah. So then the first example, the result from the function that is returned is a pointer, a pointer that points to a long data type. All right, or a pointer that holds the address of a long data type. Does that answer your question? Okay, yeah. So the first one is not at all a function pointer. It's just a normal function whose name is function. Whereas the second one is a function point. Right? Any doubts on these two declarations? The main rule that you need to remember when you create a pointer to function is the parenthesis over here. The parenthesis does need to bind the asterisk and the name of the function pointer, because as you can see the difference between the two, when there is no parenthesis there, this becomes a normal function. It is not a function point. This is a normal function whose name is function and which returns a long pointer. All right. So yeah, I hope you're all okay. I can't see anybody messaging or anything, so I think I'm good to go. Okay. So this is where so in these sort of declarations, as you can see, it is a long declaration over here. So whenever you have a longer declaration where you have multiple data types, where you have multiple arguments in your function pointer declaration, you can make use of the type def that we just saw, which will help you to define a new name for an existing type. So in these cases where you see that the function pointer is really long, you can create a type def for that, for those function pointers. So before we see the type def, we'll just see how these function pointers can be called. All right. So in the case of in the case of pointers, how we would dereference a pointer was just give an asterisk sign and call the pointer name, right? So it would be something similar to this. But in the case of function pointers, the asterisk is not necessary. You can just call the name of the function and give it the argument. So say you have a function pointer called p_func. This is a function pointer because you have tightly bounded with the parent. So you have the asterisk and the p_func. And then, so this is this p-func is a pointer to a function that takes an integer argument and returns a long data type. So assuming this p-func is holding the address of another function. Now the way I could invoke that function is just make a normal function call as like you would do for for any normal function call. So to use the name of the function, use the name of the function pointer in this case. So you would say p-func and pass some argument there. So it is similar to how you would make a normal function call. Even in the case of calling this function pointer, you would just treat it as a normal function call. All right. Okay, so p-func is your DJ. All right. Okay. So yeah, hope you've understood the way you could dereference, the way you could access the function pointed to by the function pointer, the way you would access the addresses. Just call the function pointer. All right. It is similar to how you would call a normal function call. Use the name of the function, and in arguments, give the argument that you want to pass. So when you say p-func ix, it will make a call to the function whose address that this function pointer holds, argument ix to it. So you could either say asterisk p-func or just p-func. So it's up to you. All right. So that is the way you would make a function call. I hope that's clear. That is the way you would make a function call that is held by a function pointer. Okay. Now the reason I'm going a little slow is because I'm also checking the messages in between. Okay. So I hope you're clear with the function pointers. Now you're also allowed to create arrays of pointers or arrays of function pointers. All right. So how would you create an array of pointers, array of pointers pointing to integers? How would you create an array? Just give the number in, give the data type, the name of the variable, and give the size in the dimension. Give the dimension there in your square bracket, right? So if you want to create an array of pointers to integers, just give an asterisk sign over there. So if you say int asterisk p int array and the dimension 10, basically means you're creating an array of 10 pointers to integers. So in this array, this 10 sized array, each value in there is going to hold an address of an integer. All right. It is an array of pointers where each value in the array hold the address of some integer variable. So similarly, to create an array of pointers to functions, because a pointer to a function has to be tightly bound in this manner, you would say asterisk p-func array. But along with that, you will also need to give the size and you will also need to give the dimensions in square brackets. Okay. So if you want to create an array of pointers, maybe 10 array of pointers to functions, you would say asterisk p-func array, and in square brackets you would give 10. So this will constitute an array of size 10 where each pointer is a function pointer that will point to a function that will hold the address of a function that takes two arguments and returns a void data type. A void data type basically means that it does not return any data. All right. So each of those values in that array to contain is going to take, each of those values in that array is going to be a pointer that is the address of a function holding two integer pointer arguments and which does not return any data because it is a void data type. So are you clear with these two declarations, especially the second one, the array of pointers to functions? Okay. Are you guys listening at all, or have you totally lost it?
Yeah.
No,
Um,
yeah.
okay. If you want to take a break now, we can.
Hmm.
So we will continue with the rest of the lecture after at 11.
Sounds good.
All right.
So, we
And
will
so,
sing happy birthday.
So this is like a Google form.
We can't see it.
We'll
We
set
need
it out.
permission.
Can you not see my screen now?
Oh, we can
Why
see
is
it.
that?
Yeah.
Okay.
We just tried to open it. You
So I
can
put the.
see it.
You're not able to open it?
No.
I posted a picture of what we
Right.
get.
Okay, maybe let me just see if I've given the permissions or not. Didn't I give any? Mm, Just give me a minute. I'll just disconnect for 2 minutes and I'll just. Okay, Hamish, I'm just reading the last message. Then separately, I have copies of the solution. I have also an exe for the release build. Is that all the files? Yeah, that's all the files. But make the files are all that. But make sure you do not change the project structure. So when you try to delete files and when you try to move it here and there, do not change the structure of the project itself. All right, do not move files from one place to the other. The only file you're allowed to move is the release build executable. That is the only thing you can move. The other files, the other unwanted files, can be deleted, like the .idk, the .pdb, and delete off the debug folders, the release build folders. The only thing you need is the release build executable. So that is the only one you're supposed to move out. If you touch the project folder structure, remember the project is not going to open up properly. So if the what I'll be clicking is I'm going to be clicking on the SLN file, the solution file. So when I double click on the solution file, the Visual Studio project should open up without any problems. So before submitting, make sure when you click on the solution file, it opens up the Visual Studio project. All right, whatever is your submission format, take a copy of that and make sure when you click the solution file, take a copy of it before opening the solution file, because if you open the solution file and if you build it again, remember the debug or the release folders are going to be generated again, which you will again need to delete. So take a copy of your final submission zip, and then see if you're able to, if when you double click the solution, you are able to open the project without any problems and run it. So do not touch the project folder structure otherwise. So what else do you have? Can you clarify the files to include? So the files to include, rather than clarifying the files to include, I think what will be easier to say is what files you should delete from. So remove these sort of. I hope you can see my screen. I've gone live, haven't I?
There you have.
Okay. All right. So remove these sort of files, wherever you find the .obj, the .pdb, the .idk. Remove the debug folder. Remove the release build folder after you have copied the release build executable. So take out the release build executable and copy it in another location, and then delete off the entire folder. Everything else, that is the .cpp, the .sln, the .vcx project, all these should remain there in the same structure. Do not change it from its positions. Just remove these sort of extensions, the .obj, .pdb, .ilk. For now, I believe these must be the only maximum extensions you'll be having, and of course the debug folder and the release build folder after extracting the release build executable. Okay, and like I said, also put in a README. README is a text file, so put in a README along with the release build executables. So that will give me that will contain the instructions of how to run your project and what your project is. Of course, I know what your project is, but that is how you would write a README generally. So you would, in brief, just explain your project and what the controls of your project are. Do we need to zip every folder or just the main folder? Just the main folder. You'll have to zip the release build executable. So like you can see over here, it's slot machine hyphen your name dot zip. So the this release build zip should contain your release build executable and the README text file. All right. The project, that is a source project, which the source file, the source hyphen student name over here is where your project is. So you don't need to zip that. Put the slot machine, put the release build executable zip and your project folder into a main folder and name it in this format. That is the YYY, MMDD, GD1, PO1, mini project, so on, and zip that up. So yep, that is Hamish. Yeah, your structure seems to be fine. I mean, I can just see your final zip. Yep, the naming format from what I can see looks fine. If something goes wrong with submission, will we have time to fix it and send the correct file or not? Yeah, I'll try to You have time. I mean, your deadline is like 6 p.m. Friday. So I'll try to check out all the files on Saturday. I'm not going to be marking it on Saturday, but I'll be just briefly checking it just to make sure I can open all your project files and I'll be able to run it. So if I have a problem with that, I'll be contacting the ones with the problem so that you can resubmit it. But when you resubmit it, you're not allowed to make any change to it. So the the date stamp in this case is very important. So the only thing you're allowed to do is just submit it as it is. Can we submit it a day? I need to check. Yeah, that'll be a good idea. Yeah, bravo. You can submit it a day earlier, and the others also. Don't try not to keep it until the last minute. I can have this inside that folder. That is slot machine. So I'm reading Hamish's message. Slot machine. What you're supposed to zip is the. Maybe there's something wrong with the settings. Hamish, I don't understand what is your. If you just the source source hyphen
Did you just say that to a
your name is supposed to contain the project itself, so you do not need to zip that. What you need to zip is the slot machine.
Did you just say that to a
I'm
teacher?
talking about this part over here. You're supposed to zip this one here. What will contain the release build executable. All right, you only need to zip up that. You don't need to zip up the project folder. And I don't know what the slot machine folder in your pick indicates. You've got two folders there, slot machine hyphen your name, and the second folder, slot machine. I don't know what the second one means. All right. The brief says use pointer and arrays for the marking. Do we need to include even though it's not in marking schedule? We just okay. I don't remember. Wait, let me just have a look at the brief myself. Are you talking about this part over here? Is it this one here that you're talking about, Reese? Okay. See, this is the objective of the assessment in the sense that you can use it if you want. This is not the expectations. So this is just this is basically the outcome of the assessment. That is, if you use it, I mean, you have the capability to use it. But since the marking criteria does not specify it, you're not going to be marked down if you don't use it. All right. But I mean, it's just that you have the ability to use it for this project. So that is basically the assessment outcome. Or, I mean, yeah, the aim of the assessment, but it's not going to be marked down. Your marking is going to be purely against the marking criteria that is specified here. All right. Okay, Hamish. So yeah, I guess you're clear with that. Do you have any places would you recommend? You would recommend for hosting your files? Um, I guess the most common one is the Google Drive. The Google Drive has 15 GB free. Yeah, GitHub is also okay. So yeah, GitHub. Yeah, it's better if you get used to GitHub now because you will be using that extensively in your coming years. Or even Google Drive is fine. That'll give you 15 GB. But Google Drive is just a temporary solution. Okay. So is that all from slot machine hyphen is meant to include the release build executable? Yes, it is meant to include your release build executable and the README file. All right. So put the release build executable along with the README file into this folder. Into the let me just go to that. Into the slot machine hyphen student hyphen student name.zip. I mean, put it into the folder slot machine hyphen your name and then zip it up.
I have a question about the project.
Okay.
I was able to get the slot machine to work, but it doesn't do the rolling animation, and it doesn't load onto a different screen. It just loads after the menu, and then it just comes down again like a big list. Will I get marked down for that?
You're not going to be marked down for the rolling part. The rolling part is just an additional feature of the project.
Okay.
So, but I mean, if you're able to clear the screen, it'll make it more um the- at least this part of the assessment. If you look at the interface, makes excellent use of screen space and has good visual appeal. So what we expect is at least the screen part gets cleared up every time there is a new round happening. Every time there's a new slot running.
How do you do
So
the clear screen part?
um, clear screen. There is a clear screen function also. How have the others done it? There is a CLR SCR function. There are also other ways you could do it.
Okay.
I think some of them have used the CLS. Okay, so Hamish has
CLS.
posted one system as a CLS. So try that out. There's a normal C function called SLR as well. I mean CLR SCR, I guess. Yeah, but try out the system CLS.
CL
CLS. Yeah,
CLS.
yeah. The
That's a.
way the others have posted on the channel. All right. The main thing is please get the game functional first. The game should be functional for you to reach until the A. So that is the most important thing. These things are, of
It
course, from the
works.
UI point of view.
It doesn't have. I don't know how. And it was a screen clear. It was.
Mm,
I
your
screen
message is
counting.
not coming out clear. Do you want to type it out instead? Was it Lisa who was talking?
Doing it on my.
Okay. If anybody's talking right now, I'm not getting any message. I'm not able to hear you.
No one's talking at the moment.
Okay, all right. So, okay. Is there any other doubts? Just going back. Okay, after the lecture, I'm gonna put my files in the right folder. Okay. Um, okay. It's good if you try to.
Sorry,
Okay,
one second.
just
Lisa's just ducked
yeah,
out.
I can see many of you are trying to make the slot machine spin, but remember that is not the main functionality. The main functionality is getting it to work. So work on these additional stuff only after you've done with the entire functionality. That is what carries marks. It's only if you're able to cross until the A that you will go into those A plus level. If you just do the rolling of the slots, but you don't the expected functionality in the C, B criteria are not satisfied, then you're not going to go up to the A plus. So please focus on getting all these marking criteria to be satisfied first before you go into the running of the slot. Your slot is 3 times 3. Yeah, that's fine. So the middle one, Hamish, for the middle one, I assume is the one where you show the final slot, right? You can win based on all three lines. Okay, you can maybe give me the description. I might need the description in the README in this case. All right, okay. So this is the reason why your README is really important, because you might have different ideas for your games. And it's not just the README. Even your even your UI should show me clearly what the about what the controls are and how I could win the game. So you should treat me like a normal player. If I go to a slot machine, if I go to play the slot machine, or maybe some arcade or something, I'll be getting my instructions only from what I see on the UI. The controls are intuitive. Mm, if it is intuitive, yeah, of course, you don't need too many instructions. But probably it's just intuitive to you because you're the one who has developed it. So that is one thing you'll need to take care of. The README is still very important. Yeah, the README is always required. The README is always required for every project that you make. Going forward, whenever you ask to submit projects, please make sure you also create the README. It should be part of your project. All right. Even if your controls are intuitive, the README is very important. Controls are intuitive. Maybe the instructions on the UI uh, can be reduced, but try to run it with another person and see if he is able to understand how your game is. I mean, without your help. My controls are bad in the program, but are still listed. If your controls are, what do you mean by bad? See, whatever your controls in the program, please show those controls on the UI. The README is just for the is actually is not the first thing that I'll be looking into. So if I'm a player, I don't have a README document with me. What I'll be reading is only what is on the UI. So your UI also should be explaining your controls, not in detail, just the required stuff. So you wouldn't expect any player to read through the entire instructions over there. So UI should be more visually understood by any player. You've been constantly able to intuitively know what to do. All right, Nera, so if you have tested out with a few people, then I think it should be fine. But like I said, the README is a more descriptive one, which is required for every project. So that is something that should be part of your project. And Hamish, I've shown them, but okay. All right. I hope I've not missed out any message. Okay, so before we waste any more time, I've got some more lecture to get done. And yeah, so I'm just going back to the where is the I'll need to pin up the the Google form link. I've lost it myself. Where did I post that? Probably just be easier to copy it. Okay, so I'll pin this up. please use this link to submit your project. If you do not have any upload server, if you do not have a host server, then um, still fill in the details in there and then send me your project. So this will help me to keep track of how many of you have submitted the project. When you open your link, it should open to a Google form in this manner. So you enter your email address, your first and last name, and the link that I need, that I'll be clicking to download your project. Once I've downloaded your project, I'll send you a message. You can stop sharing it with me. All right.
Um,
So
which
yeah,
which email do you want us to use? Our personal one or our school one?
that doesn't matter. Just use any email because that is the email I'll be using to contact you. All right. Um, what is more important, use your full name over here, your first name and your last name, because that is how I'll be marking you. The email address that you specify is the email that you are available at, so that I can reply and yeah, message you for any information that I require. I have my school email set to forward messages to me. All right. Your Give me the email address that you will be looking through frequently. All right. So that was about that. Can we continue with the lecture, or we'll run out of time? All right. Okay, so far we had seen about arrays of pointers to integers and arrays of pointers to functions. So I hope you are clear with that. So whenever you declare a pointer to function, remember you need to give the pointer name and the asterisk within the parenthesis. So it has to be tightly bound. So these two have to be the asterisk and the pointer name should be tightly bound. When you want to create an array of pointers to give the dimension also parenthesis. So give the dimension in square brackets like you would normally create a point, like you would normally set the dimension for an array. So give all that, and then the remaining is about specifying the type of function that is going to point to. So the type of function that contains two integer pointers and which has a return type void. In other words, which doesn't return. All right. So that's about pointers, arrays of pointers, arrays of pointers to functions. So um, the places where these pointers to functions are as widely used is whenever you have, for example, like Windows events. So you can have multiple events that goes to these windows. So it's like a mouse event, a keyboard event, um, I mean mouse click event, mouse middle button click event, or maybe a system event, and so on. So in each of these events, if we set a function pointer that that holds the that keeps track of these events that comes up at particular intervals, and then we send these information to the relevant function, then what we need to do is we just need to create a single pointer to a function, and that pointer to function decides which function to call based on its runtime value. Whenever I use the term runtime, it basically means the value that happens while, I mean, the value that a variable gets when the program is running. All right. So when you run the program, that is when the runtime comes into the picture. So at runtime, looking at the value, looking at the event that is held by the pointer, it can decide which function to call based on that event. So that is where pointers to functions, a pointer that can hold the address of multiple functions becomes useful. So you can see an example over here. There is a print values function which takes as arguments a function pointer. So how do you know this is a function pointer? Because there's an asterisk in parenthesis. All right. We don't have a name here because this is just a prototype or declaration. If you remember, a function is specified in in two ways. One is a function declaration or function prototype, which is to tell the compiler that there is a function of this name. There's a function that contains so many arguments and this return type, and that will be defined later on in the program. So this has to be done. This function prototype or declaration should be above the point of call, the point of function call. So at that point, it's not necessary that you give the function that you give the names of the argument. Though of course it is a good practice to give the names because then everybody will be able to understand what is the intention of these arguments. All right. So over here, if you give something like int and another int asterisk, it's not clear to another programmer about what inputs this print values is going to. So it's always helpful to give the names rather than just give it this. So this is a valid C++ prototype, a valid C++ function prototype, but not quite helpful for other programmers to understand. So it's always best that you give the names as well. So the actual purpose of this function is function pointer that takes two integer point arguments and that returns and that has a void return type, and has two more arguments which are integer pointers and that takes in ix and iy. So it is probably the x and y coordinates that whose address it is storing, probably to print the values. Right. So that is most probably the purpose of this function. So this is how you can take a function pointer. So the reason we're going for a void asterisk function pointer so that it can um, is is so that it can point to every function that takes two arguments and that has a void return type. All right. So that is this function here. So yeah, this sort of declaration is probably used infrequently, but then if it is used, like for example for Windows events, it will be much easier. All right, because it makes it much easier to call the func. You just need, it's like a controller. So you have, I mean, when I say controller, I'm not talking about the Xbox controllers. I'm talking about like a sort of manager. So a manager who keeps track of what events are coming up, and then he delegates the task to the responding to the respective functions. He delegates what all tasks he get to the respective functions. So these function pointers will help you to keep track of the coming events and pass it to the relevant functions for further execution. So in the case of these function pointers, it will be much helpful to use a type def because in case of long definitions, if you want to create multiple function pointers, it is going to be kind of difficult. So each time you will need to do void as name of the function pointer and then give an arguments int asterisk, and so on, and then assign it to, and then make it hold the address of another. So rather than do that, we can create a type def. So a type def looks similar to a function pointer, but is actually not a function pointer. So in this case, when you say type def void asterisk VPF, and then you have the, so what it means is it is giving a type def name called VPF to a function pointer that can point to a function that holds two integer pointers and returns a void. All right. So this is actually a type def definition and not a function pointer definition. So when you have the type def keyword before that, remember that you're giving an alias name to this function point. And after that, it's pretty simple. You just use the alias name VPF and save. So whenever you use the alias name pfunc, what it means is you are basically creating a function pointer that is called pfunc. All right. So what this means internally is I'm just trying an app over here just to uh okay, it doesn't work. Okay, so what this statement here means is that, so internally what it means is void void asterisk, so that is your asterisk p func. I know my handwriting is a bit mm, okay, this is not working with me. It's all right, we'll just forget it. So this is basically void asterisk p func, and in brackets, because I don't have any space here, I'm going to the next line. So it's int asterisk. So this is what this internally means. All right. So here pfunc is a pointer to a pfunc is a pointer to a function which returns a void return type and which has two arguments, that is in which has two integer pointer arguments. Maybe I want to create another function called instead of pfunc, I want to create one more called rfunc. So I'm changing this to rfunc. And then I want to create one more called maybe x and so on. But the return type and the argument list remain. So I want to create three different functions over here. But each time if I have to write this entire thing, it's going to be a little bit of a cumbersome. And that's where this type def is quite. So if I create one type def saying that these sort of declarations, call any of these sort of declarations, I want a pointer that has two integer pointer variables and which returns a void return type as VPF, then it's pretty easy for me. I can just say VPF p func the first time, then I can say VPF r func the next time, VPF x func the next time, and so on. The basic type of the function remains the same. I'm talking about two integer pointers and a return type is void. So Hamish, why is VPF p func made in main? Because in main I'm creating a function pointer. It's like creating a pointer variable. So later on in the main function, I will be using this pointer, this function pointer. It's just like creating a normal pointer variable. So in my main function, I'm going to be doing, maybe I'm going to be assigning pfunc to the address of some function with the same function signature. Okay, all right. So I hope this is clear now. The type def just makes it easier for us to create a function pointer of the same signature without going through the cumbersome process of writing the entire function signature. All right. When I say function signature, I'm calling up function arguments and the function return type. So I don't have to write the entire function signature each time I make a function pointer of the same type. So in those cases, create a type def and make your life easier. Not that you would use function pointers too often, but if you have to. All right. So yeah, this is what I was talking about. It's mostly used in event-driven programming environments with Windows. So if you want to check for clicks, for double clicks, mouse events, and so on, you would have an event handler, and this event handler is a function that gets executed based on what event has passed through it. All right. So whenever you detect an event, you can make use of this function pointer, and the function pointer, based on the value that it contains, will decide which handler it should send the or which handler it is supposed to call. And when it calls the corresponding handler, the handler takes care of what to do next. All right. So that is where the function pointer, that is one of the important users of a function. So yeah, that was what is there in this lecture. So we have seen about constant keyword, constant, and about we have seen about constant pointers, about how a constant pointer can point to a non-constant variable, and how a variable and how a normal pointer could point to a constant variable, and how a constant pointer could point to a constant variable. And then we had seen about type defs, which is basically alias names for your data types. So any data types can have an alias name just using the type def keyword. And finally about function pointers, which are basically pointers to functions with a function signature. So yeah, that's about this. Do you have any doubts on this? Work through the exercises. I know you guys will be busy with the project now, but once you're done with the project, please work on the exercises. This is the only time that you get to strengthen your programming skills. So the exercises are really helpful in that. Please type out each of the exercises and make sure you uh, go through each one and see if you have. There's also one more lecture which is a very important concept, and that's about dynamic memory. Going forward, dynamic memory is something that you will be using quite a lot. So let's start off with this. Okay, so before we see about dynamic memory, we'll be just seeing how the memory is divided into different sections and where my dynamic memory is used. And finally, about what memory leaks mean. All right. So, like I said, there are your memory space is divided into multiple spaces. So, if you remember what global variables are what you declare outside any functions, so that is able to be accessed by all the other functions. All right. So each of these global variables are stored in something called a global namespace. So there's a different section of memory that takes care of your global variables. And the next is registers. So registers are what stores the internal data such as the stack pointer, the instruction pointer, wherever like where it keeps track of all the internal registers. And this is where your the pointers to your, like for example, the function stack and stuff are stored. And then comes the code space, which is a space where your program code is stored. The stack, the stack is where which contains the memory for all of your local variables. So any local variables that you create within your functions or within the argument, within the function argument list, all of these are stored in the stack. And finally, the free space, which is the heap memory. So it is a heap store that we'll be seeing in detail today. Bravo is writing a message. Is that something for me? Let's just wait for his message. Is anything created before the main a global type? Before the main, if you have any global variables, yes, that is stored into the global namespace. All right. And when you say before the main, all your entire code, including the main, is stored in something called a code space. Structs um, structs are basically blueprints. So it's like defining a data type. All right. So unless you create a structure variable out of it, or a structure object as you can call, or maybe a class object, if you create that in the global space, then that will go into the global namespace. Otherwise, if the object or the variable is created inside the function, it's going to be going into the stack. So that depends on where you create the variables. All right. Neris. Okay, I can see a couple of you writing something. Variables defined as members of a class. Variables defined as members. See, these variables get memory only after you create an object out of a class. So that depends on where your object, where your class object is created. When you define variables as members of a class, the memory space for that is not allocated yet. It's just a normal code. So that goes into the code space. It's only when you create an object out of this class that memory is allocated for it. And depending on where you create this object, if you create the object inside your function, then that memory goes into the stack. The entire memory for all the variables in your class is in the stack. If you create it globally, the entire memory is going to be in the global space. Yes, all the people. Hamish, yeah. Everybody creates structs in global. Yeah, that's right. But that does not mean that the memory is allocated immediately. The memory gets allocated only when you create objects out of it. Okay. Generally, then the program pulls things from the code space and puts it on the stack. Um, yeah, the code space is where you can refer your port. So the program is going to refer to the code space to see, to execute the instructions in the code. Yeah. Okay. All right. So I guess we are good to go in that case. Okay. So now, like I said, what we'll be discussing in detail over here is going to be about the free store. So the reason we are going for free store is, the main reason is because when we create an array, I guess few of you had asked me about the same question before. When you create an array, you will need to immediately decide how many spaces or how many elements that array should contain. Like for example, if you want to create an array for the number of players in your game, you don't know how many players are there in your game, so you're just giving a random 100. So probably the number of players are just 20. But then, since you don't know how many players that game could have, you're just giving a maximum value of 100. So in other words, you are wasting 80 spaces over there because only 20 spaces are going to be used up. Or probably the players go beyond 100. So you have maybe like around 150 players, but you've just allocated 100 spaces because you assume that it would never go beyond 100. So in those cases, creating arrays is a problem, because what you would need to do now is you would need to create a new array with a new size. All right, but that can only be done in code. You would only know at runtime, only you would only know when you run the program that, okay, these are the number of players that I require for my game. Now I'll need to change it. But that facility is not there for arrays. In the case of arrays, you will need to specify in the code about the size of the array. So since array doesn't have this flexibility of looking at runtime and finding out how many players are actually there and then resizing itself, in those cases, using the free store is very helpful. So Neris, can't you make a dynamic array with pointers? Yeah, that's what we're going to be discussing now. All right, we are going to be creating going to be allocating memory to solve this problem. So only dynamic. Once the array is created, it won't be able to change. No, once the array, that's the problem with arrays. Whenever arrays get created, you won't be able to change the size of the array. So that's the reason we have to look for an alternative solution, right? So an example is this one given over here. So one of the drawbacks with arrays is that their size is fixed. For example, this is illegal. So you can see how um, we are asking the user to enter the element that we want in the array. So you have C in it, and then I'm trying to do float array n. So if you try out this code, this is going to throw you a compile time error, because it is important for the compiler to know at compile time that how many spaces this particular array requires. Okay, based on the number in the square brackets, the compiler understands how much memory is supposed to be allocated for this array. But since you've said float array n, the value of this n is only obtained at runtime, because it is only when you run the program that the player can say the element value. So the compiler has to wait till runtime to know, and the compiler doesn't function at runtime, and that's why this is going to throw you an error. So what you could do for to solve that issue is just specifying a maximum value in the dimension, which is a wasteful process, because that could waste lots of memory, or maybe that is less than the current size. All right, and that's why we would be going for the free store. So the free store is a large area of memory that can be used to store the data. So the free store basically gives you the freedom to allocate only as much size as you require. So a free store gives you the gives you the ability to actually look, to wait till runtime, get the runtime value, and then create its size based on the value that you obtain at runtime. All right, but when you use the memory from free store, it's like a step-by-step process. You need to request memory first from the free store, and then after you have used it, it's your responsibility to return that memory back to the free store. So it's like you're requesting um some additional maybe money or something from a higher authority. So you keep that until you want, and then you've got to return it. And it's your responsibility to free the memory after you've used the program. All right, after you've used it, after you have done with its usage. So I'm just looking at your messages. It's only so Callum says once the array is created, it won't be able to change. No, Callum. So um, if you had created an array with a specified size, yeah, that is going to be the size. That is going to be its size forever. So you won't be allowed to change the size of that array, and that is where this heap store comes handy. And there is C++ does not have automatic garbage. Okay, yeah, all right. So yeah, the advantages of a free store are you don't need to pre-allocate all variables. That is, you do not need to decide at runtime how much storage is required, or how much memory you need to give for each variable. Whenever you reserve memory, the memory is available until you basically release that memory. So it's like you keep it for some time. After you've done it, it's your responsibility to return it. Because if you don't return it, then that memory is available with your program until the end of it. So so imagine like around 100 variables requiring free store memory. So 100 times you take memory from the free store memory, from the heap memory. The free store is also called the heap memory. So you take memory from the heap, and then you keep it with you, but you do not return it even though your usage is over. Ultimately, this heap store memory will get exhausted, and that's why it's very important that you return the heap store memory as soon as you're done with it, because the lifetime of that heap store memory is throughout your program. All right, so until your program ends, the heap store memory is not returned. So it is your responsibility to return it so that other functions can use, or other variables can make use of the heap store memory whenever required. And how do you allocate, or how do you request memory from the heap store? Using the new keyword. All right, so this is the one here is basically how you request memory from the heap store. Just say new and the data type that you want. All right, so it's basically a pointer that can request a memory from the heap store. So you have the pointer defined over here, and that is equal to the keyword new by the name of the point. Or in other words, you have the example here. So does if you want memory for an integer variable. So you just say int asterisk the pointer name is equal to the keyword new followed by the data type int. And that is the way you obtain memory from a heap. If you want a floating point, if you want memory for a floating point, the only changes you have float asterisk, maybe fn, maybe p float is equal to new float, and that's as simple as that, right? So what it is going to do is it's going to take, in this example, it's going to take 4 bytes of memory from the heap and then return it to this pointer. So the pointer contains the address of an integer location in your heap memory. So the pointer points to an integer location inside the heap memory, or points to a 4-byte memory in your heap that is supposed to hold an integer value. Okay. So what is the difference between requesting memory from the heap and not just using the stack? Because the stack is allocated memory only during compile time, whereas a heap can wait until runtime and then allocate memory based on what the runtime input is. So in the case of arrays, for example, you can see how much input the user requires. Like for example, you the player says that he needs memory for 20 players, or there's going to be 20 players in the game. So you get the input 20 from at runtime, and then based on that input, you request 20 space of memory from the heap. So the heap memory is the only way that you can get the required memory at runtime. The stack memory works only at compile time. Is that clear? So this is most useful in those cases where you want to wait for the runtime input first before getting memory from before allocating some memory. I'll just wait for those who are typing. So when you compile with a stack, it uses all that memory. But if you use a heap, your program, yeah, that's right. When you use your heap, the program can request memory only when it needs it, and only that much amount of memory as much as required. Whereas in the stack, whether you need it or not, you know that sometime in the program you will need it. But so that's why you will, and you don't know the amount of size that's required. So maybe I might just say, okay, 100 spaces of memory always. Okay, because I'm not sure about how much memory is required and about what point, but then I will have to create it if I was going for arrays. So right, so it's for when there's an external input that decides something. With the, yeah, that's right. So this is basically to help you just use the right amount of memory based on the runtime input. Okay, I can see lots of you are interested with the heap memory. Okay, I'll just maybe take one more doubt and then I'll go forward because it's almost 12:15 now. And yeah, if using the heap, is it possible for an external program to use that memory making? Is it possible for an external program to use that memory making it sweep? Mm, it depends on who. I'll need some more clarification with that question. So okay, either Hamish or Calum, do you want to go unmute now and then ask me your question one by one? Because I guess that'll be faster than typing it out. There's One of you, can you go on unmute? Because then it'll be clearer to me about what your question is.
I think Hamish is asking if it's possible for the memory that your program wants to allocate from the heap
Yeah.
to clash with another program that's running allocating the same memory and causing a problem.
No, that's not going to happen. That's why we said that whenever there's memory obtained from the heap, you'll have to return it when it is done. Because otherwise, if lots of programs are making use of the memory and nobody returns it, then we are going to run out of heap memory. So there's not going to be a clash on the heap memory. All right. Once you use it for your program, until you return that memory, it is going to stay with your program. And that is throughout the lifetime of your program. Once your program ends, then that means then it is only then that the memory goes back. Or you will have to explicitly say, which is a practice that you'll need to follow. Whenever you take memory from the heap using new, you have to practice to also return that memory once you're done with its use. Yeah, so only yeah, that's right. Poorly designed programs will not be returning memories, and that's when we get exhausted out of the heap memory and the heap memory finally returns a null. So in the case of pointers, whenever something fails, like we saw in the casting, like we saw in one of the casting, the dynamic cast, whenever a casting fails, it returns a null. So the same happens over here when the memory allocation fails, it returns a null to the pointer, which indicates that the heap memory is exhausted and there is no more memory to be returned to the pointer. So you can see the example over here. Whenever you use the new to obtain memory from the heap, it's also very important to check the value in the pointer. So if you say if not pint, the pointer is not, it basically is to check whether the pointer is null or not. All right. So if the pointer is null in this case, suppose assuming that it hasn't obtained any memory from the heap, the pointer is null, condition would become true because the pointer is not containing any value or is null. Then you will need to maybe stop your process there and show to the and display to the user that the memory allocation has failed. So it's always important that whenever you use some external process on the pointer, you have to check for whether the pointer is a null value or not. All right. So if memory allocation fails, new will return a null pointer. So whenever you use a new, also make sure you use a delete. A delete is what returns the memory after usage into the heap store. All right. So delete returns the memory back to the heap store, free store. And this has to be always done once you're done with the usage of the pointer. So you say something like int asterisk pint is equal to new int, which is the free store allocation, and then you have done some maybe whatever functions or whatever actions you want to perform on the pint pointer. After you're done with that, just do a normal delete pint, which is your free store deallocation. All right. And after that, as a best practice, always do pint is equal to 0 after you have deallocated after you have deallocated the free store. Because right now you have given the memory back to the pointer pint. I mean, you have returned the memory back to the free store from the pint. And as we have discussed when we did pointers, a pointer should always point to either a relevant memory location or it should be 0. If it is not 0, then it is going to be a dangling pointer, and a dangling pointer is a very dangerous situation because the pointer could point to a very crucial system memory and it might cause an issue there. So if your pointer is not pointing to a relevant location, then always make it 0. That's why make this a whenever you use a new, also decide when you're deallocating that memory. Then use the delete function to return the memory to the free store. And after you have done that, to avoid dangling pointer issues, assign the pint to 0 or assign the pointer to 0. So is this clear? To allocate memory, use a new keyword. And to return the memory back after usage, use the delete. This should always be a practice. So always remember whenever you use new, decide where the delete should go and put in the delete there as well. And after that, assign the pointer to 0 if it's not going to be holding any relevant location. All right. So this is another free store example. Okay, so the main difference between static and dynamic memory allocation is that the static memory allocation is decided at compile time, and it gets automatically deleted after the block that where it was created gets destroyed. All right, or it ends. So maybe you've created your when I say static memory allocation, maybe I'm talking about an array that's allocated, or maybe a normal variable. So any variable that is defined within a block or within a function gets destroyed after the end of that block or after the end of that function. So that automatically happens. But in the case of dynamic memory allocation means the heap memory allocation. In the case of heap memory allocation, it is destroyed only when the programmer explicitly destroys it using the delete keyword. If the programmer does not delete it, then this stays throughout the lifetime of the program. So even though the function or the block where you have used the new has ended, it still does not get destroyed. It waits for the entire program to get over. So the lifetime of this heap variable is throughout the program. So it's going to be a poor design if you do not delete it after usage. All right. So yeah, in this example, you've got p float is equal to new float, and then as usual, what you're doing is if you want to assign some value to the to the memory allocation which is pointed to by the point, dereference that pointer using the asterisk symbol. So asterisk p float is equal to 2.5f. So it dereferences assigns a value 2.5f into the into the address where it's pointed to. After I'm done with that, I'm just doing a delete because I want to give the memory back. And since I'm not doing anything else with p float and I don't want it to be a dangling pointer, I'm saying p float is equal to null pointer, or you can also simply say p float is equal to 0. All right. So that is an example of free store. So this is something that you'll be using for a lot of things forward. All right.
Why do you have to set the pointer to null when you delete it?
So that if your pointer is not going to be holding a proper memory location, then it's important that you assign to 0 so that it doesn't point to any crucial memory address or crucial system address.
So when you delete it, all you're doing is deleting the memory allocation. You're not
Yeah,
deleting the point.
delete is only to return the memory back to the heap store. Delete is only giving the memory back to the heap store. So that that memory, it's like saying a reservation. So you reserve some space in a maybe what do you say in your flight or something. So when you cancel the ticket, the reservation goes back and then somebody else can use it. So delete is basically just saying that I don't need this memory anymore and just take it back.
Right,
With
but the pointer will still point to that memory even after you've unallocated it, which is why you need to set the pointer to
the
null
pointer,
pointer.
you cannot say where the pointer could point anywhere in the memory actually, and we're not sure where the pointer could point to. After you have if after you've given back to the heap memory, the pointer is going to be pointing somewhere in the stack memory and not the heap, because unless it uses a new, the pointer cannot point to a memory in the heap.
Okay,
Yes,
so you need to
the pointer
so you
picks
need to
up some random memory to point to. That's right. Yeah. Okay. What were you saying?
so you need to do both of those things. You need to
You
both
will need
delete.
to do both of them. Yeah,
Okay, cool.
both of them. Okay. And always make it a practice to assign the pointer to 0 or a null pointer if you are not immediately giving it an address. Not just for a free store, not just in the case of free store, in any case, if as soon as you declare a pointer, you're not giving it an address, assign it to 0. or a null pointer, which is both the same. So that should always be a practice. Okay, so moving on to the next one. So this is about, yeah, this is an example of memory leaking. So memory leaking is happens if you allocate memory, if you allocate memory to a pointer from the heap memory, but you never deallocate it, or you never use the delete operator. Okay, so in this example, in the main, as you can see, the mem leaker is called around 500 times. So 500 times a new pointer is allocated memory from the heap. So 500 times, like, there are floating point memories uh, used up from the heap memory, but it's never deleted, and that's when a memory leak happens. You keep allocating memory, but the memory is never returned back. Okay, so at the end of this function, obviously my use to float is over, but the memory still remain, but the memory is still reserved for this function, though it can never be used. Okay, and since we have lost the pointer, we can only access the pointer from this particular function. We will not be able to deallocate it from the main, because if you come to main and if you say p2 float, main does not know what p2 float is, because p2 float only exists inside the mem leaker function. All right, mem leaker, the p2 float is a local variable of mem leaker because it was created inside the mem leaker. So it is only inside the mem leaker that you can do the delete p2 float statement, because the main has no idea what the p2 float variable is. So though the memory exists throughout the lifetime of the program, the memory can be only accessed using the pointer, and that pointer is available within this local function. So Hamish, yeah, once we leave scope, we can't get back to that pointer. No, once we leave scope, once, unless of course you return the pointer. If you return the pointer from that function, then yes, you will be able to access that memory. But in this example, you're not returning the pointer, and there's no way other function could know the existence of this pointer. There is no way there's no way you can use this. You can all right, and that's why this is a poor program. Memory 500 times, but it has taken no steps to deallocate the memory using delete, and there is no way we could deallocate the memory in any other function because p2 float cannot be accessed in any other function. So I hope you have understood this poor design. Okay. So the best practices after you've done with it, just do a delete p2 float within the same function, because I have no, in this particular example, I have no reason to access p2 float outside the function, and that's why I'm not returning the p2 float. So so the so it is the responsibility of this function, of the mem leaker function, to take care of deleting the p2 float. So I've done delete p2 float there and assign p2 float is equal to 0. Of course, this is a meaningless function. Here I'm just doing a mem leaker. I'm calling the mem leaker function, allocating memory and deleting it. Doesn't make sense, but just for an example, it's easier to understand. All right. So it's also possible to declare arrays, which is of course one of the reasons we discussed before coming here. So if you want to declare an array using the size that is available from the user or from the player, use the same format, that is using the new operator. So you have new, the data type, the size in angular brackets, in square brackets. The way you would do for a normal array. So here as an example, we have int asterisk p int is equal to new int and the size in square brackets. So the square brackets is not given for the is not given beside the pointer variable. It's given when you obtain the memory from. All right. So I've done new int, and in square brackets I've given, which basically means I am requesting memory for an integer array of size 10 from the heap memory, and the address of this is going to be given to the p int pointer. So P in pointer points to an integer array of size 10 on the heap memory. And using this P in pointer, I can access every single array or all the array elements on the heap memory. All right. Like we have said, every time you use new, we also should understand how to use delete. So in the case of arrays, if you allocate memory using with the square brackets, the delete should also have a empty square bracket. When you give an empty square bracket over there, it is an indication to the compiler that you are actually supposed to delete the entire array. If you don't give these square brackets over here, and if you just say delete pint, it's only going to free the first memory space in the array. All right. So in this example, you've got a memory space for 10 elements in your array. Simply say delete pint. It's only the first memory location of the freed. The remaining 9 spaces are still reserved. So to avoid that situation, you will need to specifically say delete and an empty square bracket. Do not give the size in there, just give empty square brackets. The empty square brackets it gives signals to the compiler that it first needs to check the size of the array and then delete all the elements in that array. So in this case, it is 10 elements in the array and deletes all the 10 elements. Or in other words, it deallocates all the 10 elements. So the delete and empty square bracket is very important in the case of deallocation of an array. And finally, p int is equal to 0. So if you leave the brackets off, remember only the first element will be deleted. And again, this is going to be a memory leak because you're just freeing the first memory and the remaining 9 elements are still not freed. So that'll be a memory leak. So don't forget the empty square brackets after delete if you're trying to deallocate an array. Okay. So these are examples, different examples. So in the first case, in test 110, here's just a normal array of 10 integers. All right, test 1 is just a normal array of 10 integers. The second test 2 over here is an array of 10 integer points. All right. What's this test 2 is basically an array of size 10 where each element is an integer pointer or each element is a pointer to an integer. Okay. So test 2 will contain each element that will hold the address of an integer variable. That is what the second line. And what about third line? Int asterisk test 3 is equal to new int 10. So as discussed in the previous slide, this is a pointer variable which requests for an array of size 10 from the heap, an integer array of size 10 from the heap. And the address of that heap memory is given to the, in other words, test 3 is a pointer to an array of 10 integers. So please understand the difference between the second and the second one is an array of 10 pointers itself, whereas the third one is a single pointer that points to an array of 10 integers. All right. So yeah, this is an example of a dynamic memory allocation. So you have this is where we come to the main use. You enter the number of elements that you want in the array, which I store in inum elements. And what I'll be doing next is I'll be just doing pi array, which is an integer pointer array, equal to new int. And instead of giving a hard coded value, what I'm giving is the inum element. So what this does is at runtime it gets the value from the user. So maybe the user says like 50. Enter the number of elements you want there. I'm saying 50. So at runtime it's requesting for 50. It's requesting for an array of 50 spaces or an array of 50 elements from the heap memory. Okay. Do whatever you want with that array. And finally I say delete an empty square bracket pi array. So this indicates to the compiler that the pi array that I need to deallocate pi array, which is actually an array. Deallocate all the array elements in the pi array pointer. And that's how the dynamic memory allocation works for a pointer. All right. So I hope that is clear. I know we have gone beyond time already, so I'll just quickly brush through the remaining slides. Maybe just another 5 minutes and we'll be done. Okay, I hope you're clear with this usage because this is the main reason we start the allocation. All right. So yeah, these are a few memory values that you would notice whenever you debug. So I hope you have started debugging your program already by putting breakpoints and then checking the memory window. So whenever you see that some values allocate on the stack but not initialized, you would see some memory value in this. This is when memory has been allocated to the heap but is not yet initialized. So these are some memory values that you can test out using your debug, using the memory window in debug. So just check that out whenever you have the time. All right. And yeah, this is an example of the dynamic memory summary. So dynamic memory, as you can see, you can get the input from the user and then allocate memory dynamically using value entered by the user. When you're done with its usage, don't forget the delete square brackets and the name pointer. And this is an illegal operation if you try to allocate memory, if you try to use your normal um, array declaration value entered by the user. So if you were to do something like float array, and this is a normal stack memory. A normal stack memory cannot allocate memory based on the user input, and that's why this will throw you a compile time error. All right, so this is when your dynamic memory allocation from the heap becomes handy. And we're done with that. So yep, static memory is what we have learned so far. That is for all that is for any local variables, for all function arguments, for arrays and stuff that we create within the functions. It all goes into the static memory. And if you want to allocate memory based on a runtime value, please go for the free store memory. And that is done using the new keyword. But after your usage, make sure to always return the memory back to the heap, because otherwise you will be encountering a memory leak situation. A memory leak means when you do not return memory to the heap, and finally, because the heap memory could get exhausted, because the heap memory exists throughout the lifetime of your program. So deallocate memory after your usage using the delete operator. And if you are deallocating the memory of an array, use the empty square brackets along with the delete operator. All right. So that was the summary about dynamic memory allocation. I guess you won't be using it now, but then once you're done with the project, please work on the exercises and find out other situations where you could use it. All right. So if you have any doubts, do message me or ping me or whatever you find convenient. I know I've taken more time than required. Otherwise, for any doubts, just ping me and I'll get back to you as soon as I'm online. All right. Anything that you want to ask me right now? Any doubts from today's topics or any doubts about the project?
Uh, um,
Yeah.
Sorry.
Yeah.
No,
Did you
I'm
want to
good.
ask something?
Oh, no. I just unmuted by accident. Sorry.
Okay. All right. Okay. Yeah. Thank you to you guys for listening. And yeah, follow the please enter the details into the Google form that I've just pinned into your channel. Submit your projects via that. I can keep track of how many of you have submitted. I'll get back to you once I have downloaded it successfully. All right. If you're done with the projects, maybe submit it before Friday. Don't wait until Friday. We can submit. Yeah, you can submit using any drive, but just give the link clearly in the link description. All right. Okay.
Thank you.
So thank you for attending the lecture. And yeah, have a good 2 week break. So we'll be seeing after 2 weeks now. All right. So see you in
Thank you.
2 weeks' time.
Cool. Thank you very much.
Thank you.
Before you
Yeah.
log off, can you please pin in the chat uh, an example of the screen?
Can you maybe type what you're saying because your voice is coming through clearly? Can you message on this channel? When do we get the test back? Um, the test is not the marking is not yet complete. So sorry about that. Just things got a little hectic after we started going online. Um, let me see. I mean, of course, now we do have the 2 week break, but then it should be done by then.